Large language models have demonstrated impressive performance across a wide range of use cases. While this is largely due to their immense scale, deploying these massive models to solve real-world problems can be challenging. In this video, I'm going to discuss how we can overcome these challenges by compressing LLMs. I'll start with a high-level overview of key concepts and then dive into a specific example with Python code. And if you're new here, welcome. I'm Shah. I make videos about data science and entrepreneurship. If you enjoy this content, please consider subscribing. That's a great no-cost way you can support me in all the videos that I make. Last year, the mantra in AI seemed to be bigger is better, where the equation for creating better models was more data plus more parameters plus more compute. And we can see over time, large language models just kept getting larger and larger. This is a figure from reference 11 down here, and we can see over time models kept getting bigger and bigger. So in 2018, large meant something around 100 million parameters. In 2019 with GPT-2, we were up to 1 billion parameters. Then came GPT-3, which was around 100 billion parameters. Then we have more recent language models which have 1 trillion parameters or more. There's no doubt that this equation actually works. GPT-4 is objectively better than GPT-3 and everything that came before it. However, there's a problem with creating bigger and bigger models. Simply put, bigger models come with higher costs. So just to put this into computational terms, 100 billion parameter model is going to take up 200 gigabytes of storage. And then if you want to use this model, you got to fit this massive thing into the memory of your machine. So needless to say, this comes with high compute costs. So it's probably not something that'll run on your laptop. You're going to need a lot more compute than that. It comes with higher financial costs. And then of course, it comes with a higher environmental cost. But what if there was a way we could make these large scale models a lot smaller? This is the motivation of model compression, which aims to reduce the size of a machine learning model without sacrificing its performance. So if we're able to pull this off by taking a massive model and shrinking it down to a smaller model, this means we could run one of these models on our laptop or even on other devices like cell phones or smartwatches or other types of devices. Not only does this foster greater accessibility for this technology, it also promotes user privacy because these models can be run on device and user information does not need to be sent to a remote server for inference. This also means less financial cost, and of course, the negative environmental impact can be a lot smaller. Here I'm going to talk about 3 different ways we can compress these models. The first is quantization, the second is pruning, and the third approach is called knowledge distillation. Starting with quantization, although this might sound like a scary and sophisticated word, it's a very simple idea. Quantization consists of lowering the precision of model parameters. And you can think of this like taking a high resolution photo and converting it to a lower resolution one that still captures the main features of the image. And to put this into computational terms, you might take a model whose model parameters are represented in FP32, so using 32 bits, and translating the parameters into int 8. Just to get a sense of this, the number 7 represented in FP32 looks something like this. So the computer has to keep track of all these binary digits just to encode a single parameter. However, if that same parameter is represented in int 8, that'll look something like this. It's a fourth of the memory footprint. If you want more details on how quantization works under the hood, I talk more about it in a previous video of this series on QLoRa. I'll link that here for those who are interested. When it comes to implementing quantization on large language models, there are 2 popular categories of approaches. The first is called post-training quantization. And the basic idea here is you train your model and then quantize it. The key upside of this is that this allows you to take models that other people have trained, and then you can take them and quantize them without any additional training or data curation. Using this approach, you can take these off-the-shelf models that might be encoded in FP32 and convert the parameters to 8-bit or even 4-bit. However, if you want to compress beyond 4-bit, post-training quantization typically leads to a degradation in model performance. performance. For situations where even more compression is needed, we can turn to another set of approaches known as quantization-aware training. This essentially flips the order, where one quantizes the model first and then trains it. Training models in lower precision is a powerful way to get compact models that still have good performance. This means parameters can be encoded with even fewer than 4 bits. For example, in reference number 6, the authors were able to create a 1-bit model that matched the performance of the original llama model. But of course, the downside of quantization-aware training is that it is significantly more sophisticated than post-training quantization because one has to train the quantized model from scratch. The second compression approach is pruning, which consists of removing unnecessary components from a model. So an analogy here is that pruning is like clipping off dead branches from a tree. It reduces the tree's size without harming it. To put this in terms of parameters, we might have a 100 billion parameter model, but then through pruning, we might reduce it down to 60 billion parameters. While there are a wide range of pruning approaches out there, they can be broadly classified into 2 categories. The first is called unstructured pruning, which consists of removing individual weights or parameters from the model. Showing that visually, if this is our original model here, unstructured pruning might consist of zeroing out these 2 weights in the model. The key benefit of unstructured pruning is that since it's operating on this granular scale of individual weights, it can result in a significant reduction of non-trivial model parameters. However, there's a key caveat here. Since we're just taking model weights and turning them into zeros, this is going to result in sparse matrix operations to get predictions from our model. In other words, the matrix multiplications involved in generating a prediction from our model will consist of a lot of zeros. And this isn't something that normal hardware can do any faster than non-sparse matrix operations, which means that one needs specialized hardware that's designed to optimize these sparse matrix operations in order to realize the benefits of unstructured pruning. On the other hand, we have structured pruning, which instead of removing individual weights, it removes entire structures from the model. This can be things like attention heads, neurons, or even entire layers. So visually what this might look like is if this is our original model, we might remove this entire neuron from the model, which does not result in the sparse matrix operations that we see in unstructured pruning. While this does result in less opportunities for model reduction, it allows one to completely remove parameters from the model. If you want to explore specific unstructured and structured pruning techniques, check out reference number 5, which provides a nice survey of these approaches. The final way we can compress an LLM is via knowledge distillation. This is where we transfer knowledge from a larger model into a smaller one. This is just like how we all learn at school, where we have a teacher who has much more experience in a particular subject, transferring their knowledge to the students. In the context of large language models, the teacher model might have 100 billion parameters, which are then distilled to a student model, which might have just 50 billion parameters. Again, there are a couple of ways that we can achieve this. The first is using soft targets, which consists of training the student model using the logits from the teacher model. What that means is, let's say we have our teacher model here, and let's say it performs sentiment analysis. So given a chunk of text, it'll label that text as either positive sentiment or negative sentiment. The way these models work is that the raw outputs are not just a positive or negative prediction, but rather there's a prediction for each class known as a logit. For example, let's say the logit for the positive class is 0.85 and the logit for the negative class is minus 0.85. What this is indicating is that the input text is more likely to be positive sentiment than negative sentiment. And this is exactly how text generation models like Llama 3.1 or GPT-4 work under the hood. However, instead of having 2 output logits, these models will have tens of thousands of output logits corresponding to each token in its vocabulary. These logits are then converted into probabilities, and then these probabilities can be sampled to generate text 1 token at a time. So we can actually use these logits to do knowledge distillation. So the way that works is we'll take our our smaller student model, have it generate predictions, and then we'll compare those predictions to the teacher model's predictions for the same input text. And the reason these are called soft targets is because the predictions of the student model aren't compared to a 0 or 1 ground truth, but rather a softer, fuzzier probability distribution. This turns out to be an effective strategy because using all the output logits from the teacher model provides richer information to the student model to learn from. Another way to achieve knowledge distillation is instead of using logits to train the student model, one can use synthetic data generated by the teacher model. A popular example of this was the alpaca model, which took synthetic data generated from the original ChatGPT and used it to perform instruction tuning on Llama 7B. In other words, ChatGPT was used to generate these input-output pairs of input prompts from users and output responses from the model, which were then used to endow this Llama 7B model with the ability to follow instructions and follow user prompts. So now with a basic understanding of the key concepts behind model compression, let's see what this looks like in code. As always, the example code here is freely available on the GitHub. Additionally, all the models derived here and the dataset used for training is also freely available on the Hugging Face Hub, and we'll be using Python for this example as well as PyTorch. The example here is we're going to take a text classifier and compress it using knowledge distillation and quantization. So that's one thing I actually forgot to mention, is that these three different compression approaches of quantization, pruning, and knowledge distillation are often independent of one another, which means that we can combine multiple approaches to achieve maximum model compression. So here I'm going to combine knowledge distillation with quantization to achieve a 7x reduction in model size. The first step here is to do some imports. Many of these are Hugging Face libraries, so datasets is from Hugging Face. We'll import some things from transformers. We're going to import some things from PyTorch, and then finally I'm going to import some evaluation metrics from scikit-learn. Then I'll import the dataset with one line of code, and this is something I've made available on the Hugging Face Hub. It consists of a training, testing, and validation dataset with a 70-15-15 split. So it's 2100 examples of data in the training dataset and then 450 examples in the testing and validation. And the dataset consists of two columns. The first column are website URLs, and the second column is a binary label of whether that URL is a phishing website or not a phishing website. So this is actually a very practical use case used by email providers or cybersecurity folks that may want to ensure that links are safe before presenting them to end users. With the data loaded in, we'll load in our teacher model. Here to speed things up, I used the freely available GPU on Google Colab. So I'm importing that GPU as a device here. Next, I'm going to load in the teacher model, which is a model I fine-tuned on this phishing classification task. We can load in the model's tokenizer and the model itself using these two lines of code here. And then using this to method, I'm loading the model onto the GPU. Then we can load in our student model. So here we're going to create a model from scratch. I'm going to copy the architecture of Distilbert to initialize the model. However, I'm going to drop 4 of the attention heads from each layer. Additionally, I'm going to drop 2 of the layers from the model. In other words, each attention layer has 12 attention heads, so I'm going to reduce that to 8. And the original architecture has 6 layers, and I'm going to reduce that down to 4. Then I'm going to use this Distilbert for sequence classification object. What that does is it'll load in this Distilbert architecture with these modifications and then slap on top of it a classification head. In other words, the model, instead of generating text, is going to perform text classification. We're also going to load the student model onto the GPU. And just to get a sense of the scale here, the teacher model has 109 million parameters and takes up 438 megabytes of memory, while the student model here consists of 52.8 million parameters and takes up 211 megabytes of memory. The reason I'm using relatively small models by today's standard is that this is what I can easily run on the free GPU on Colab. But if you have beefier GPUs or more compute at your disposal, you can take this code and just plug in bigger models and it should work just fine. So the dataset that we loaded in consists of plain text with a label label. So before we can actually use this data, we'll need to tokenize it. Here I defined a simple pre-processing strategy. So what's happening here is each URL is being converted into a sequence of tokens. The tokens are being truncated so they're not too long. And then within each batch of examples, the shorter sequences are going to be padded so all the examples have the same length. And this is important so we can convert it into a PyTorch tensor and efficiently do the computation with the GPUs. This is the pre-processing function. The actual transformation happens in this line of code. So we take the data set and then we map it into tokenized data, making sure that we are using batches. And then we're converting it into a PyTorch format where we have columns for the tokens, the attention mask, and the target labels. Another thing we need to do is define an evaluation function. So this will allow us to compute evaluation metrics during model training. And so there's a lot happening here. So I'm going to go through it line by line. First, we're putting the model into eval mode instead of training mode. We're initializing two lists. One list is for model predictions. Another list is for labels. Here, we're going to disable gradient calculations. Then batch by batch, we're going to do the following. First, we're going to load all the data onto the GPU. So that's the input tokens, the attention mask, and the labels. Then we're going to perform the forward pass. So we're going to compute model outputs, and then we're going to extract the logits from the outputs. This logits variable here will actually consist of two numbers, one corresponding to the probability that the URL is phishing, and another corresponding to the probability that the URL is not phishing. So in order to turn this into a binary classification, in other words, the URL is phishing or is not phishing, we can take the argmax of this logits variable, and then that'll be our prediction. And then we can append the predictions and the ground truth label to these lists we initialized earlier. Once we do that for all the batches, we can compute the accuracy, precision, recall, and F1 score for all the data in one go. Next, we're going to define a custom loss function. And the way we're going to do that is we're going to use both soft targets, in other words, the logits from the teacher model, and the ground truth labels. And so the way we're doing that here is we're going to compute a distillation loss as well as a hard loss, and then we're going to combine those into a final loss. So to get the distillation loss, we'll first compute the soft targets. So these are the teacher's logits, and then we're going to convert those logits into probabilities. In order to generate probabilities from the teacher model's logits, we can use the soft max function, and it's common practice to divide the teacher logits by a temperature parameter, which will increase the entropy of the probability distribution. So we generate a probability distribution corresponding to the teacher's prediction, and then a probability distribution corresponding to the student's prediction. And now that we have two probability distributions, one from the teacher model, one from the student model, we can compare their differences using the KL divergence. PyTorch has a built-in method that does that, so we can just easily compute the difference between these two probability distributions using this line of code here. And then we can compute the hard loss. So instead of comparing the student model's predictions to the teacher model's predictions, we're going to compare them to the ground truth label. And then we'll use the cross entropy loss to compare those probability distributions. And then finally, we can combine these losses by adding them together and adding this alpha parameter, which controls how much weight we're giving to the distillation loss versus the hard loss. Next, we'll define the hyperparameters. So here I use a batch size of 32, put the learning rate as 0.0001. We'll do 5 epochs. We'll set the temperature that we use in our loss function at 2. And then we'll set the alpha, so the relative weights of the distillation loss versus the hard loss, as 0.5. So we'll give equal weight to both types of losses. Then we'll define our optimizer. So we'll use Atom. Then we'll create two data loaders. We'll have a data loader to control the flow of batches for the training data as well as the testing data. Then we'll train the model using PyTorch. So we put the student model into train mode and then train it. We have two for loops here. So we have one for the epochs, one for the batches. And it's a similar thing as to what we saw in the evaluation function. So we'll load each batch onto the GPU. We'll compute the outputs of the teacher model. And then since we're not training the teacher model, there's no need to calculate gradients. So we can avoid that using this syntax here. Then we'll pass through the student model to generate its outputs and extract its logits. We'll compute the loss value using our distillation loss that we defined earlier. And then we'll perform the back propagation. Sorry, the script was too long, so I had to extend it like this. But once we make it through every single batch, we can print the performance metrics after each epoch. So we'll print the accuracy precision recall F1 score for the teacher model, and then the accuracy precision recall F1 score for the student model. And then we'll be sure to put the student model back into train mode because this evaluate model function that we defined earlier puts it into eval mode. So I know this was a ton of code, maybe way more code than you were hoping to get into, but here are the results of the training. So we have 5 epochs here, and we can see the loss is going down, which is a good sign. So it bumped up in epoch 4, but then it dropped back down in epoch 5, which is very normal. And then we can compare the performance of the teacher and student models. So of course, since we're not updating the teacher model, its accuracy is going to stay the same across all epochs because it's not changing. But we can see the student model performance get better and better across each epoch. And then once we get to epoch number 5, the student model is actually performing better than the teacher across all evaluation metrics. Next, we can evaluate the performance of the teacher and student models using the independent validation data set. So the training set is used to update model parameters. The testing data set is used in tuning the hyperparameters of the model, and the validation set wasn't touched. So this will give us a fair evaluation of each model. And for that, we again see that the student model is performing better than the teacher model across all evaluation metrics. This is one of the other upsides of model compression. If your base model, if your teacher model is over parameterized, meaning that it has way too many internal parameters relative to the task that it's trying to achieve, actually compressing the model not only reduces the memory footprint, but also it can lead to better performance because it's removing a lot of the noisy and redundant structures within the model. But we can go one step further. So we did knowledge distillation. Let's see how we can quantize this model. First, I'll push the student model to the Hugging Face hub, and then we'll load it back in using the bits and bytes integration in the transformers library. So we'll use the bits and bytes config. So we'll load it in 4-bit. We'll use the normal float data type described in the QLoRa paper. And all this is a clever way of doing the quantization to take advantage that model parameters tend to be normally distributed, so you can be a bit more clever in how you quantize the values. And I talk more about that in the QLoRa video that I mentioned earlier. Next, we'll set the compute data type as BrainFloat16, and then finally we'll do double quantization, which is another thing described in the QLoRa paper. Once we set up this config, we can simply just load in our student model from the Hugging Face hub using this config file. So the result of that is we have still the same number of parameters, 52.8 million, but we've reduced the memory footprint. So we went from 211 megabytes down to 62.7 megabytes. Then comparing that to our original teacher model we started with, we cut the number of model parameters in half, and then we reduced the memory footprint by about 7x. But we're not done yet. So just because we reduced the model size, that doesn't mean that we still maintain the performance. So now let's evaluate the performance of the quantized model. Here we see we actually get another performance gain post quantization. So intuitively, we can understand this through the Occam's razor principle, which says that simpler models are better. So this might be indicating that there's even more opportunity in knowledge distillation for this specific task. All right, so that brings us to the end. If you enjoyed this video and you want to learn more, check out the blog in Towards Data Science. And although this is a member-only story, like all my other videos, you can access it completely for free using the friend link in the description below. Additionally, if you enjoyed this video, you may enjoy the other videos in my LLM series, and you can check those out by clicking on the playlist linked here. And as always, thank you so much for your time, and thanks for watching.